Alright, this is Mr. Gillum, and today we're going to talk about tangents. Do some tangent notes, and we're going to learn a few properties of tangent lines. Alright? A tangent is a line that touches a circle in exactly one point. Okay, and we call that point the point of tangency. And so this circle has a lot of different tangent lines to it, but all of the tangent lines are only touching the circle in one point. So in this case, line AB would be tangent. It only touches there in only one spot. I'm not very good freehand, but if I drew a line perfectly right there and it connected just with that point on the edge, that would be a tangent line. If I drew a point perfectly right there, this would be a point of tangency, and this line would be a tangent line. So there's many tangent lines. The quality that makes them tangent is that it touches the circle only in one place. All right. Sometimes circles have what we call a common tangent, okay, where the line is both tangent to the small circle and the big circle, or the circles share that point that the line is intersecting. All right. So a line, ray, or segment that is tangent to two circles in the same plane is called a common tangent. So it is tangent to both these circles in exactly one point. There are several common tangents to these circles that we're going to look at here right now. Looks like line L is a common tangent to F and G. If I drew one this way and it was tangent right there and right there, that would also be a common tangent line. Or on this one, we could do this guy. It could be a common tangent line. Or that one. So there's a lot of different ways to do it. As long as it is tangent to both circles, then we call it a common tangent line. So in this case, we have some common tangents. It says to draw them. Well, okay. Let's think about this. If I can draw perfectly, just like that, that would be a common tangent line. I could draw this common tangent line, maybe. Did it just right. It would touch right there and right there. That would be a common tangent line. And because these circles are intersecting, I believe those are the only two common tangent lines that we have in this case. All right. Similarly, it looks like the same exact two circles, except now they're not intersecting each other at all. So my common tangent line, I could have one just like I just drew right there, where it touches exactly right there and exactly right there. I could have a tangent line like so, where it touches exactly right there and exactly right there. I could also have a tangent line. Oops, it's very not good. Okay, I could also have a tangent line in between the circles, like so. Boom, boom. Right there, or in the other direction. Right there and right there. And actually, it's hard for me to draw perfectly tangent lines when I'm drawing on this huge overhead, but you get the idea, I think. In this case, there are 4 common tangent lines to those two circles. All right. Now, sometimes there won't be any tangent lines that are common, which is fine too. And if that's the case, I believe in the homework it says just say that there's no common tangent lines. Tangent lines are the shortest distance, I should say. A tangent to the center of the circle is a radius drawn to the point of tangency. It just so happens that if that is the case and the line is tangent, then the radius of the circle to the tangent line will form a 90-degree angle. So this little guy right here is important. Everything comes back to those 90-degree angles. All right. I know that this line is perpendicular to this circle because the distance from the radius to the line, the perpendicular distance, touches at the point of tangency. So if it tells me that JL is a radius of J, and to determine whether KL is tangent to J, I need to justify my answer. Well, I know from this last theorem that we just talked about that if this KL is tangent to the circle, then I know this must be a right angle. And so it looks to me like we got a diagram here of a right triangle if, and only if, it is actually tangent. So the goal is to prove that this little guy right here is a right angle. Well, because I know this is a radius and a length of 8, I also know that this highlighted blue part has a length of 8, because all radii of a circle are congruent. And so what I have here ideally is a triangle with the sides 8, 15, and 17. And so luckily for us, we just took a test on this. Yes, this is the possible lengths of a triangle. What type of triangle is it? Well, ideally, hopefully, it'll be a Pythagorean theorem, and in this case, it's actually a Pythagorean triple. But we can show that this is a right triangle by using the Pythagorean theorem. 8 squared plus 15 squared should equal 17 squared. If you know your Pythagorean triples, it'll be much quicker for you to do. So I know that, 289 is equal to 289. Then the two triangles, this specific triangle with lengths 8, 15, and 17 is in fact a right triangle, guaranteeing me that this KL is tangent to J. All right, so I've guaranteed that this must be a right angle. All right, take a look at another one here. It's kind of like the other way of thinking about it. It says JH is tangent to circle G at J. Find the value of X. So using this information, it is tangent. I know for sure that the radius to the tangent line makes a 90-degree angle with the JH. So I'm going to go ahead and draw that 90-degree angle in. And that's really the only difference there. As far as solving this problem compared to the last one, you need to be conscious of if it's tangent, the radius is perpendicular to the tangent line. Okay, so this part right here, we just need to make sure we know that that means that the radius to the tangent line is perpendicular. So now we just have a Pythagorean theorem exercise. I have a leg, and a hypotenuse. I'm going to say that x squared plus 12 squared must equal the total length of this side. We're going to represent by x plus 8. X plus 8 squared. And then it's just a matter of doing my algebra. And please don't change that to x squared plus 64. We do need to separate that into two parts and double distribute. Okay, do not take the easy way out and say x squared plus 64. Obviously, you would be leaving out the 8x and the 8x. So don't do that, please. X squared plus 144 is x squared plus 16x plus 64. Now, we talked about how to solve quadratic equations before in this class. Luckily, though, when I subtract x squared from both sides, it's no longer a quadratic equation, meaning a degree of 2. It's now a linear equation. And I can solve for the x. You see it takes a little bit of work here for some of these problems. I expect to see that work on your paper as well. It does say to find the value of x. It doesn't say specifically to find the hypotenuse or anything like that, or the radius. So I can stop right there. The value of x is 5 in this case. All right. So again, the big idea is that if it's tangent, then the radius is tangent to, or is perpendicular to that tangent line. If two segments from the same exterior point are tangent to the circle, then they are congruent. So this one's a pretty good little theorem to have. I know that if AB is tangent and BC is also tangent, then AB is congruent to CB. All right, congruent, and it would make sense that it is congruent. Okay. So you're looking for that point where those two congruent lines touch. From that point to the point of tangency is always a congruent segment. So in this case, if it says segment AB and CB are tangent to circle D, find the value of x. Well, if they are both tangent, boom, 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 right there. The last term that we just talked about says that, well, if it's tangent from the same point, the point to that segment, the point to the point of tangency is congruent. So I know that x plus 15 must be equal to 2x minus 5. And again, we just have a linear equation here to solve. (20) equals x. And again, it just says to find the value of x. It doesn't say find the length of the segment from the intersection of the tangent lines to the point of tangency. It just says find what x is. That's what we've done. We're good to go there. Okay, so from the point of the tangent lines intersecting to the point of tangency, those parts are congruent. Finally, we have a little word problem here. We love the word problems. It says a graphic designer is giving directions to create a larger version of a triangular logo shown. If triangle ABC is circumscribed about circle G, find the perimeter of ABC. So I'm looking for the perimeter of this entire triangle. So I need a length for this side, and this guy. Okay, so let's use our information that we just learned about the tangent lines. It looks to me like BE is 7 and BF is another point of tangency. And I know it's a point of tangency because it says it is circumscribed. Okay, it's circumscribed, meaning it touches right there, right there, right there, and only in those places. Okay, only 1 point for each one. Each of these lines is tangent to the circle, and this is the keyword that tipped me off to that. So I know that this is 7, then this guy is 7. And I know the whole thing is 10, and 7 of it is used, so that means this guy is 3. And I know that this is tangent. So from there to there must be congruent from CF must be congruent to CD, so that must also be 3. And finally, AD, that section, is also congruent to that section. This must be 8. So if I'm looking for my totals to help me find my perimeter, I know that I have 3 plus 8 is 11 feet. I have 8 plus 7 is 15 feet. And I have 7 plus 3, and actually already gave me that length of 10 feet. So the perimeter of the triangle is 11 plus 15 plus 10. In this case, that equals 36 feet. That's the perimeter. Alright, so that's it for today. You should know a couple things about tangent lines now. It means it touches the circle in one spot and only one spot. There's some common tangent lines, and there's also some properties about the point of intersection of tangent lines and the distance to the point of tangency. So that's it for today.